welcome to A2Z Physics and Chemistry. So today we are going to discuss about capacitor and capacitance. A capacitor mainly consists of two conductors separated by dielectric. Okay, so let us consider two capacitor. Okay, capacitor 1 and capacitor 2, and there is charge. Suppose the charge between them is Q and minus Q. And the potential is V1 and V2, and the charge is Q and minus Q. Okay, so normally we are taking the charge Q and minus Q, and the potential difference is V1 minus V2 between the two conductors. Okay, so in this case we know by using a battery or by connecting a battery to the two terminal of the capacitor or by the two terminal to the conductor, we can charge the capacitor. Okay, so the important thing is that we know the electric field. The electric field by using Coulomb's law 1/2.70 Q by R square. Okay, we know by Coulomb's law, also by using superposition principle, also we can say the electric field will be equal to 1/4.70 Q by R square. That means here E is normally directly proportional to Q. Again we know E equal to V by D. That means V is also directly proportional to Q. Okay. Now this Q by V is a constant, which we can say the capacitance. Q by V is a constant, and this C is called as the capacitance. Again repeating, a capacitor mainly consists of two conductors separated by a dielectric. Normally the conductor has charges Q and minus Q, and the potential difference between them is V equal to V1 minus V2. And we have to connect a battery to the or we have to connect the capacitor to the two terminals of the battery to charge the capacitor. We know from the Coulomb's law E is directly proportional to Q. Again we also know that E is directly proportional to V. V means the potential difference. Now so we can write down V is directly proportional to Q. That means this Q by V is constant, which is nothing but the capacitance. Okay. Now the capacitance, the unit of the capacitance will be equal to Coulomb per volt, or we can say this is SI unit of the this capacitance is farad. Okay, the unit of the capacitance is farad, but this farad value is very high. So normally in practical cases we are using picofarad and the microfarad, nanofarad, like that. This farad value is very high. And the capacitance of a capacitor normally depends upon the geometrical condition, just like shape, size. Okay, shape and size. It never depends upon this Q and V value. Rather, it only depends upon the shape, size, and the dielectric of the intervening medium. Okay, so this is called the capacitor and the capacitance. So from the formula, now we can say that the C will be equal to Q by V. That means the capacitance of a capacitor should be large when the V will be small. Okay, C will be large, as C is in this case C is inversely proportional to V. So it is when the capacitance of a capacitor will be large when the potential difference is very small for a given charge. Or in other word we can say the capacitance of a capacitor will be large, then the charge occupied by or charge carried by this capacitor will be more when the V value will be equal to very small. Okay, so we can prove this statement also. When the V value is high, then the capacitance of the capacitor will be equal to low, and the charge contained by this capacitor will be equal to low. Now how we can prove this? That means suppose we are applying a very high potential to the region between the two conductors. That means we are applying a high electric field. This high electric field will neutralize, or the high electric field will ionize the air and the surrounding medium by neutralizing the effect of the charge in between the two conductors. That means now the charge will be equal to less, and so that in this case the capacitance will be equal to less. That means when the value of the V is high, at that time the charge will be less, and the capacitance will be equal to also less. Okay, so for getting high or large value of the capacitor, we have to make the potential difference very small value for a given charge. Okay, so this is capacitor and its capacitance. Normally capacitor is used to store charge. Okay, capacitor is an element in the circuit normally used, and it is used to store charge. And another important parameter which we can say is the dielectric constant. Dielectric constant. So this dielectric constant means the amount of electric field that a capacitor can withstand without damaging it. It is an important parameter in determining the capacitance of a capacitor, and this dielectric constant means the amount of electric field that a capacitor can withstand without damaging from its normal operation. Okay, so this is capacitor and its capacitance. Next we have to switch over to parallel plate capacitor. Parallel plate capacitor. Parallel plate capacitor. So this parallel plate capacitor normally consists of two conductors. That means suppose the area will be equal to A. Here also the area will be equal to A. Suppose the surface charge density is sigma and this is minus sigma. Suppose there is an electric field which we are applying over here. Okay, so a parallel plate capacitor normally consists of two conductors separated by some distance. In this case, there are two cases. First, in the first case, we are not taking anything. That means here the intervening medium is a vacuum, and in the second case, we have to introduce a dielectric. So first, the parallel plate capacitor mainly consists of two conductors separated by some distance, and in this case there is a vacuum in between the two conductors, and the area of the both of the conductors is A, and the electric field applied will be equal to E, and sigma and minus sigma, these are the surface charge density. Okay, this is called as the charge density actually. Okay, now we know the value of the we can say the first we have to calculate the E value. So as this is conductor 1 and this is the conductor 2. For conductor 1, the net electric field will be equal to E equal to sigma by 2 epsilon 0 minus sigma by 2 epsilon 0. Why this is sigma by 2 epsilon 0? This is the application of the Gauss law also. So the next net electric field will be equal to sigma by 2 epsilon 0 minus 2 sigma by epsilon 0, which value will be equal to 0. Now for the conductor 2 also, the net electric field will be equal to sigma by 2 epsilon 0 minus sigma by 2 epsilon 0, which will be equal to 0. But in this case, this is a positive charge. As we know, this is polarized by the electric field. Now this is negative charge. Okay. So now in this case, in between the two conductors, the net electric field will be equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. So this will be equal to sigma by epsilon 0. Okay, that means in between the conductor, the net electric field will be equal to sigma by epsilon 0. We have got the value of E. Again, we know E equal to V by D. Okay, now implies D equal to E into D. Now we can apply this value. This is sigma by epsilon 0 into D. Okay, so in this case we can say this is V equal to sigma by epsilon 0 D, but we know that this charge density will be equal to Q by A. Now this will be equal to Q by A epsilon 0 into D. So we have got the value D will be equal to Q by A epsilon 0 into D, because this sigma is called as the charge density, which is the ratio of the charge carried by the surface, Q by A. Okay, now this is the value for the V. Again we know that the capacitance will be equal to, which is the constant value, which is the ratio of the Q by V. Now putting this value V, this is Q by A epsilon 0 and this is D. Now this will be equal to, or we can say this is a value V equal to E into D, or here also this value will be equal to D. We have multiplied over here. So now this is A epsilon QD by A epsilon 0. So QD, now we are getting the value. This will be equal to Q into A epsilon 0. The A epsilon 0 will be coming to the now numerator part. This is QD. Now Q cancel. The value will be equal to A epsilon 0 D. That means the capacitance of a capacitor will be equal to A epsilon 0 by D when there is a vacuum in between the conductor. Now next we have to check what is the capacitance of a capacitor if we introduce a dielectric of value K in between the two conductor. Okay, so this is the parallel plate capacitor when there is no intervening medium or when there is a vacuum in between the two conductor. The answer is A epsilon 0 by D, where epsilon 0 represents the permittivity of the medium. Okay, or permittivity of the vacuum in this case. Now we are introducing a dielectric in between the two conductor. So just now also during the parallel plate capacitor, when there is no medium, at this situation we have got that the net electric field value will be equal to sigma by epsilon 0. Okay. Now the V value will be equal to, we have got this is V equal to E into D, and this is sigma D by epsilon 0, and this will be equal to Q D by A epsilon 0. Okay. D value we have got, and similarly we have got the value. This C will be equal to now A epsilon 0 by D. Okay. Now let us introduce a dielectric in between the two parallel plates. Okay. So when we are applying a dielectric in between plates, then it will polarizes both of the this dielectric by introducing this dielectric. When an electric field is applied to this dielectric, then it polarizes the dielectric, and the surface charge become sigma p and minus sigma p. The surface charge density become sigma p and minus sigma p. Okay. Now the net surface charge density will be equal to sigma minus sigma p between the two parallel plates. Okay. Now we can find out E will be equal to, as we know, E will be equal to, every time we are calculating, this will be equal to sigma by sigma p minus epsilon 0. In the previous slide we have got the value E equal to sigma by epsilon 0. As we are introducing a dielectric, now by applying electric field, it is polarized due to this net charge density will be equal to sigma minus sigma p. So E will be equal to sigma minus sigma p by epsilon 0. Now we know V will be equal to again E into D. Okay. Now this sigma minus sigma p by epsilon 0 into D. Okay. The value we are getting, this is the potential value we are getting, sigma minus sigma p by epsilon 0 into D. And again for a linear dielectric, we know that the sigma minus sigma p value is directly proportional to sigma. Okay. Now sigma minus sigma p will be equal to sigma by K. When K represents a dielectric having a constant, this is called as the dielectric constant. K represents the dielectric constant. Now putting this value in this equation, we are getting, this is sigma by K into D. Sigma by K into D into epsilon 0. There is epsilon 0 value, because for sigma minus sigma p we have put this value sigma by K. Now this E will be equal to Q by D again, and here also we can also by sigma we can write down this is sigma QD by A epsilon 0 K, because sigma, this is called as the surface density, which will be equal to Q by A. Now putting this value, this is Q by QD A epsilon 0, and there is K. Okay. So now putting this value, we can get this will C will be equal to again Q A epsilon 0 into K by QD. Now taking Q cancel, this will be equal to A epsilon 0 K by D, and we know that this epsilon 0 K represents the permittivity of the medium, and this will be equal to every time epsilon 0 by epsilon. When K equal to 1, this epsilon 0 will be equal to epsilon. But now we have to put that the epsilon, in this case K will be equal to epsilon 0 by epsilon 0. When K equal to 0, epsilon 0 equal to epsilon. That means the dielectric constant is the ratio of the your permittivity of the medium, you have the ratio of the permittivity of the medium to the permittivity of the vacuum. Now this epsilon 0 K value we can write down here, or we can say epsilon 0 value, this we can write A epsilon by D, or we can also as usual write this will be equal to C equal to K into A epsilon 0 by D. If we are taking this A epsilon 0 D value small c, now this C will be equal to K into small c. That means when we are introducing a dielectric constant K, then the capacitance is increased by a value of K. Okay, so during the calculation of the parallel plate capacitor, we have assumed two cases. In the first cases, in between the conductor, we have introduced or we have not taken any intervening medium, or we have taken a vacuum. But in the second case, we have introduced a dielectric having a dielectric constant K, then the capacitance is increased by a factor K. So today we have discussed about what do you mean by capacitor, what is capacitance, and the capacitor depends on normally shape and size, and or you can say geometry of the system, and we can say it will depends upon the dielectric of the medium. Okay, that means it depends upon the nature of the medium. Also we have discussed about dielectric constant, then we have discussed about the parallel plate capacitor, and there we have assumed two cases. In the first case, we have not introduced anything. That means we have calculated the capacitance due to the vacuum. When a vacuum is present between the we are introducing a vacuum in between the two conductor, and in the second case we have applied a dielectric having a dielectric constant of K. Okay, so this was today. I hope you all enjoy my classes. You are enjoying my classes. Thanks for watching, and so do subscribe my video.